Hello everyone, welcome to today's lecture. We're going to talk about regulation and control. How many of you have a background in that field? How many of you study electrical engineering or cybernetics or something like that? Just one, two, three, okay. So for you guys this may be a very easy lecture again. But I guess for the rest, it serves as an introduction to the field of regulation and control. And it's an important piece for system simulation, as today's systems, such as the car example from yesterday or the aircraft heating and ventilation system we saw yesterday, need to have some sort of regulation and control to make it work, right? And this is why we need to deal with that. We will, however, as opposed to what you guys, I guess, have studied in your studies, we will not deal with very complex stuff such as the Bode diagrams, Nyquist diagrams and all that. We're going to take it on a more easy level, just sufficient for this course. These Segway things here are quite common these days. I guess you have seen that in Trondheim already, or may have used some of those. Do you feel confident to model one of these Segways with what you have studied so far? What you have learned so far with regards to Bondcraft modeling and stuff? Probably not, because it requires, as just mentioned, some sort of regulation and control, which we haven't dealt with so far. I guess many of you have also seen this example here. If you try to balance a stick, for instance your pen, on your hand and prevent that from falling to the ground, you guys actually perform some sort of regulation and control, right? Your brain sort of controls your hand in order to keep that thing stable. In fact, if you use a pen, it's actually really difficult because it's way too short. The longer the stick, the easier it is to keep it stable. As a side note, Lego, I guess all of you know Lego. They have these Mindstorm things nowadays, which incorporates some sort of regulation and control functionality. There are controllers and servos and actuators, which you can assemble to robots. For instance, this one here. Oops. This is a robot pretty much similar to the one-wheel bike example we had in the exercise number 3, I think it was. Remember, we modeled the system with regards to the vertical direction, but in reality, to make that stable and prevent it from falling off to the ground, you actually need to control it with regards to the horizontal direction, to the plane, right? And this is something you can do with Mindstorm. And as mentioned yesterday, unless you have a topic for a group project already, we have one of these boxes, Mindstorm boxes, available. And first come, first serve. If someone wants to do something like this in the group for the group project, just let us know. I guess most of you have done that already, filling a glass of water. Again, this is just a very simple example for regulation and control. By using the water tap, you sort of activate that actuator, the lever, open that valve, you fill up the glass up to a certain point, and then your brain realizes, oh, full. Because your eyes, the sensors, realize there's a certain level of water in that glass. and you need to switch it off again, right? You need to shut off the valve in order to stop the water flow, in order not to have water spilling all over the place. Basically, control and regulation and this topic is just everywhere. I guess most of the systems you actually will deal with require some sort of regulation and control, even this very simple example. Let's take another example. This guy here is a bartender in a bar, tapping some beers. And before he starts or she starts, obviously the glass is empty. And the first thing to do is I realize the glass is empty. My eyes, the sensors, see this, and this signal is being processed by the brain, which tells the hand to move and activate that tap, open the beer flow, just as with the water example we had. So eventually this glass of beer is filling up. And now this guy is not really paying attention, watching some ladies at the other side of the bar, maybe. And beer is spilling all over the place. So in that example, obviously, regulation and control didn't really take place, right? Because this is not supposed to happen. Let's analyze this a little bit, the individual elements of that system, which I have just briefly described. The system itself, you can consider this to be the glass, potentially part of the valve, of the beer valve, and eventually the beer which is supposed to go into the glass. There's a control variable, which is a response of the system, so to say, which is the height of the beer in the glass. Obviously, you want it to be as high as possible, but you don't want it to exceed the height of the glass, because then that thing happens, beer spilling all over the place. Another element in this picture here is the actuator, which essentially is the valve and the lever. That valve creates, or that actuator, the valve, creates a manipulated variable, which is, for instance, called M, which essentially is the area which increases or decreases when the valve is being opened or being closed, and thus allows for more or less beer flow into the glass. Prior to that actuator, we have the controlling element, or the controller, the bartender, the guy who is supposed to tap the beer. And the output of this controller is the manipulated variable, again, now with a dash. And this is basically the movement of his hand and the degree by what he or she opens or closes this valve by moving the lever up and down. That's a simple diagram how to put this picture here into pieces. And then the reference variable on the very left-hand side, this is what the bartender wants the beer level in the glass to be. You guys want it to be high as possible. The bartender maybe not that high, because that's money. But nevertheless, the reference variable is the level of beer you want the level of beer which the beer should have in the glass, whereas the control variable is the actual level of beer over time. So in general, the reference variable is a constant. In this case, definitely it is. Whereas the control variable, the level of beer over time, varies. Obviously, when you fill the glass, it starts from 0 to whatever. This here could be considered an open loop control thing, because basically you start with the reference variable, the controller does something, and then stuff happens at the very end, and this is basically it. There is no back and forth flow of information. Whereas, let's take another example. This guy is doing his job properly, filling up the beer, and then actually carefully pays attention to the level of beer in the glass, meaning his eyes, the sensors, give a signal, provide a signal to his brain. His brain, the controller, processes that signal appropriately, and eventually he stops the flow of beer into the glass. The difference to the previous picture is that now we have a sort of a measuring device, the eyes, which observe the level of beer in the glass continuously over time, and provide this as a feedback variable to the controller, as mentioned, to the brain, which automatically realizes, okay, the reference variable, which is the highest degree or the highest level of beer possible, or the level of beer I wanted to have in the glass, is not yet reached. The feedback variable is less than that. It basically computes the difference, which is termed the error, the difference between the set point, so to say, and the current value. And this error is then being processed by the controlling element, your brain, the brain of the bartender, who manipulates the actuator, the valve, in order to make this thing stop, the flow of beer stop at exactly the right point in time. And this is basically what regulation and control is all about. You try to keep a certain value, the controlled variable, stable around a certain set point, the reference variable. You don't want it to exceed that in either direction over time. There are, generally speaking, two different types of control. Take a look at this picture here. It's a water reservoir. If the valve at the outflow or at the exit here allows for continuously changing outflow over time, that level is going to change continuously over time, unless, or it's actually decreasing over time unless you put some water into this bassin, into this reservoir. The task is to keep the level constant. If you utilize a valve like this, which I guess many of you have seen already, it's a 90-degree open-close valve. It basically is a binary thing. It allows two states only, open and closed. The control action, or better to say, the control action is basically discontinuous, because you can either open the valve or close the valve, but you cannot really do anything in between. There's just 1 and 0. Now remember, there's a difference between the controller and the actuator. This is strictly speaking the actuator, which is a discontinuous type of actuator. But I think the message is clear. There's a concept of control which is discontinuous if you have the control action, if you have that as a discrete function and not a continuous function. Obviously, there's also continuous control. The difference now is, as this valve clearly shows, you can basically open and close that continuously, meaning that there's not just 0 and 1, fully closed and fully open. There's also states in between. So the control action, or the inflow profile which you can generate with such an actuator and a corresponding control strategy, control concept, is continuous over time. And if you want to keep that tank level really constant, this may be the better choice. However, it depends on many many factors which one is best. I guess such a valve is a little bit more expensive than the other one. So if money is the main thing, you might want to go for a cheap valve and accept a sort of unsteady tank level rather than something really precisely controlled. So this controlling element in an industrial environment and in technical systems may be described with certain mathematical concepts, which we will deal with today. There are a lot more different controller types than these ones here, but this is what is used in technical systems in many cases. Remember the examples shown on the first slides, where the human is basically the controller. I guess a human is not really representing one of these types. The brain basically works more like some sort of neural networks, which in fact are another type of controller. But for us, it's sufficient to deal with these here. And this is what we're going to do today. There are two different categories. There are basic types of behavior. Most importantly, the proportional controller. And then there are more sophisticated types of behavior, the right-hand side of this table, which are basically just a combination of the three on the left-hand side. And we will now go through these individual controlling elements, and we will use some examples to better understand that. This one here shows a toilet water tank. I don't know how many of you have actually taken a look into the old school toilet water tanks. It pretty much looks like this. You have a floating ball, the black one, floating on the water level. And this floating ball is connected by a lever to the valve, which controls the inflow to the water tank. The outflow of the water tank is basically something which you activate when you press the button and make the toilet flush. And that's a very simple mechanical or hydraulic mechanical system, so to say, which we're going to make use of in order to understand and sort of design a proportional and more sophisticated controllers. As a first step, let's try to identify these different elements, just as with the previous example. So starting with the system, as we have seen yesterday, basically everything is a system. So you could consider this whole thing to be one system. That would certainly be correct. But with regards to regulation and control, where we would like to identify elements such as the controlling element and the actuator and the measuring device, the system in this case is basically the water tank, excluding the valves and the lever, because at least the inflow valve, the actuator, is a separate item to be considered here. The controlling element is basically nothing else but this mechanical lever which connects the ball and the inflow valve. And then obviously we have a measuring device which you can consider, or the measurement device in this case is nothing else but the floating ball. Another word, maybe a more appropriate word, is just sensor, right? The floating ball basically measures the height of the water in the tank. So now, as just mentioned, the system's output basically is, at least the output we are interested in, is the water level in the tank, which is being measured by this measurement device, the floating ball, and then returned to the control element. The reference element in that sense, or the reference value, the set point, is basically the steady state we see on the left-hand side, right, where the valve is fully closed and the water level has a certain height. So let's start to develop a simplified bond graph model for this system first, before we deal with the other elements, the actuator, the control element, and the measuring device. The easiest way to model such a reservoir, as you may remember from the exercises, is basically just a C element, which accounts for the change in water height, or the volume in the reservoir, basically over time. And as the conceptual sketch on the project, which is projected there, shows, we have a flow source on the left-hand side, the inflow of water, and correspondingly we have an outflow on the right-hand side. This is the most simple way to model this, right? In fact, you actually should account for the resistances of the valves and the mechanical lever and all that, but in order to set up a control loop, we can deal with that system in that simplified manner. Now we have a flow source, and we have some node, which obviously needs to be a zero junction, because you might end up having some difference in flow here, right? The inflow is not really necessarily equal to the outflow, and correspondingly the water level will change, meaning the flow into the tank will change. we have some Q dot here, here, and here. If you now start to assign causality strokes, you realize that this system is actually ill-posed because we have neglected the valves. There's no R element here, which makes it a little bit inconvenient. But we can deal with that if we just steal some concept from fluid mechanics in order to solve, to close these, the system of equations that we will end up with. Before we do that, let's just translate this picture here, this conceptual sketch of the control loop, to the bond graph. What we basically need to do here is we need to use the solution, the flow in the reservoir, meaning if you divide that by the cross-sectional area of that thing, you get the water height over time. We need to take that value provide that value to some control element, which, to keep it simple, includes the actuator, the valve. And this this controller outputs a certain flow rate. So in fact, this is actually a modulated flow source, just as you have seen that modulated transformers, I think, where the ratio changes and it's not constant. The very same goes for this flow source here. It basically changes over time. And this here correspondingly can be treated as a modulated flow source or a flow sink, basically, because the outflow does not necessarily have to be constant. You could think of this process where you basically flush the toilet, the outflow changes from 0 to some value and back to 0 eventually. So what's the equation for this system? That's pretty straightforward now, as we have the 0 junction and we have the directions of the energy flows. It's basically just conservation of mass, which is the result of this bond graph here. So that's fairly simple, but as mentioned, this bond graph is ill-posed, since if you start to assign causal symbols, if you start from the ends here, you basically should end up with something like this, which doesn't really fit, right? So that's a little bit ill-posed here, which is why we use some trick, some concept from fluid dynamics to just close that system. We need an expression here for the outflow, basically, because the inflow is going to be changed by the controller and set by the controller, sort of. One simple concept of dealing with that is to just make that outflow a constant in the first place. Use Torricelli's law, which you can derive in fluid dynamics using the Bernoulli equation and then related to the cross-sectional area of the small little outlet where the outflow takes place, and G as the gravitational constant, and the height of the water at 0, for instance, at t equal to 0. That gives a physical reasonable value for that outflow when you press the button and flush the toilet. This bond graph equation here, as mentioned, it just provides the flow rate. But we are interested in the water level height, so we need to rearrange that a little bit. If we divide the flow rate, which represents the change of volume in the tank or in the reservoir, if we divide that by A, the cross-sectional area of that thing, we basically get the change of water height in that reservoir. And this is the equation which basically represents our system in a very simplified manner, but sufficient enough to deal with that from a control perspective. Now we need some expression for this control element, some equation, some relationship. Take a look at that lever. It basically translates some change in height or change in water level on the right-hand side to some change in valve opening, the left-hand side of the lever, right? So it basically is nothing but the linear relationship that we see here. There's a linear relationship between the change in water level height, or better to say the error, as we have defined it here. We have here the feedback variable, which in this case is pretty much equal to the water level height. We have that reference value and the difference, so maybe more appropriate to have a minus here. The difference is the difference between set point and the current water level height, the error. And this is being translated using some sort of constant to a controller output value, the manipulated variable. Now, if we had modeled this system in a more sophisticated way, meaning not neglecting the valve resistances and the valve mechanics and all that, we now would have some special expression for the actuator, for the valve. What comes out here is basically the change in height on the left-hand side of this lever, right? It goes, if the floating ball goes up, the left-hand side goes down. This is basically what comes out here. But what we actually need is the flow rate. That's what we are using to control this. And with a sophisticated model for this valve, you can translate this one to the flow rate, which we actually need. We're going to keep this easy and just assign or just assume a linear relationship again and make this a constant value. Let's call that K valve, which means there's a linear relationship between the controller output and the water flow we are looking for. And that's basically called or termed a proportional control behavior. The relation between the error and the manipulated variable is linear. It's the most basic sort of controller, and it has many mechanical, or there are many mechanical examples actually, such as this lever here. The problem with this controller is that, as we shall see in a short example, that it won't really solve the problem perfectly. So if we try to implement this here in Matlab, the equations we have, an expression for the change in water height and an equation based on these two relationships, we can actually solve this this problem and control the water level. Yes. So using some sort of function file, as you guys have used it in many examples now, we can. That's maybe a little bit too. We can solve that problem. What we do here is basically implement one equation for the change in water height. This one here. Q in, the inflow, is the second state, y2. So basically the solution of this second equation, which represents the controller. Now this one looks very complex. Please ignore it just for the moment and just take a look at this first term here, which is this valve coefficient, which we have introduced, this one, times the manipulated variable, which is the first term here in parentheses, minus Kp times the error. Now here we have the derivative of the error. And this is because we can also take these equations and take the derivative and write it in this way. These values are usually constant. The valve, we assume this to be linear in this case, so the valve constant doesn't change. And the controller gain also is a constant value. So we relate the rate of change of this manipulated variable to the rate of change of the effort. And the reason we do this is because in this equation we have the rate of change of the outflow, which, I'm sorry, which represents the manipulated variable here, or the rate of change of the manipulated variable. So that's basically it. The second equation is the controller. Please, for the time being, ignore the rest there. It is z to 0 in this example. And the last equation we have in this function file is the rate of change of the error, which corresponds to the rate of change of the water level height. This is because, as you can see from the control loop, the error is the reference value minus f. Now, if the reference value is constant and you take the derivative, it basically means that the rate of change of the error and the rate of change of the water level height is equivalent, which is why we can use it in this manner. Then we have some Matlab script where we assign parameters using global variables. We use this concept here to get a physically reasonable value for the outflow. We use dimensions as you would encounter that in an ordinary toilet, and we assign a certain profile for this outflow. At 0.5 seconds, the valve opens. You press the button. And in order to keep it simple and have some meaningful diagrams afterwards, we don't really investigate the case where the water tank is being emptied totally. We just assume a certain step in the outflow. So in this case, it changes from the reference value, or from the initial value, to 90% of the initial value. So there's some step change in outflow. And at 15 seconds, we release the button and set the outflow back to 0. Okay. That's maybe a little bit small. Ah, damn it. So pressing the button in Matlab generates such a result. As just mentioned, the blue dashed line is the water outflow. At 0.5 seconds, we press the button and it increases from 0 instantly in a step to 90% of the, or 0.1%, I'm sorry, 10% of the physically possible outflow. Meaning there's some water flowing out of the tank. The tank level decreases. And if we didn't have any controller, if we haven't had any controller, it would just decrease continuously until the water tank is empty completely. But now we have this controller in place. And using a gain of 0.4, for numerical value of 0.4 for this Kp factor in our controller equation, we actually managed to level out the water in the tank at something like 0.17 meters, 17 centimeters. The initial value of water in the tank is 20 centimeters. And just prior to these 15 seconds where the outflow is being set to 0 again, it almost manages to level out there. then the outflow is being set to 0, and the inflow eventually fills up this tank again. Again, the controller controls the rate of, or the flow into the tank, and eventually after something like a little bit more than 15 seconds, 20 seconds maybe, it reaches the original initial level of water in the tank. As you can see from this diagram or this result, this P-control concept has a conceptual flaw, which is that it doesn't really completely get rid of the error. The water level is not being is not kept constant at the reference value, because we have a steady offset between the reference value, which was 20 centimeters in the at T0, and our steady state value, which is something like 0.17 maybe. And we can verify this from this picture here, where if you press the button and the water sinks, this floating ball obviously will follow the water level, and it will open the valve and fill up this tank again. But it always requires a certain offset, and this leads to a steady state error with this P-control type of controller. On the other hand, this P-controller is fairly simple and straightforward, so it's being used in many cases, especially in the mechanical world, as mentioned. And it's especially used where this offset doesn't really matter. In the toilet water tank, you don't really care if there's a difference in the numerical value between the reference variable, the initial height, and the actual height. That's not important, right? So it's actually sufficient for this water tank, but it's in other cases not really sufficient. Any questions so far? Okay, then we take a break.